Hello everyone, welcome back to your favorite and India's most affordable learning platform, Physics Wala. So in the last session we have started the mechanical properties of solids, so where we already dealt 2 lectures in it. So today we are going to deal with the lecture number 3. So in lecture number 3 we are going to focus on the stress strain curve and the Poisson's ratio. So these two are the simple and short topics. So from here you will get the theory questions. Direct theory questions will be picked from stress strain curve. Okay, and Poisson's ratio is also a simple topic. So we will do some questions based on these two topics as well. Okay, so it's going to be a short lecture for today's class. So we'll cover only these two topics. So after this chapter we'll start the mechanical properties of fluids. Chalo. So let's move to the next concept. So first see the stress strain curve here. So if you draw the stress versus strain curve, so this is how the curve actually looks like. Okay, so now see in any metal, so how the strain varies with respect to the stress. Strain versus stress. Okay, so there are certain points. So this, let it be O, A, B, C, D, E. Okay, so what are all these points and in which regions so the body will retains its original position again, and at which points the body cannot return to its original point. So that we'll discuss. So already we studied about the Hooke's law. We already know about the Hooke's law, where the stress is directly proportional to strain. So where the stress is directly proportional to strain. So the stress strain curve, it looks like a straight line, right? So the graph shows straight line. The graph shows straight line, right? So here if you observe in this graph, so O to the A region, O to the A region, so the stress is directly proportional to strain. So OA region here, so it's follows Hooke's law. It follows the Hooke's law where the stress is directly proportional to strain. So even if we remove the stress, so the body will retain back to its original position. Okay, so if we remove the load, so the object retains its original configuration. So that means there is no permanent change in this region. So this A point is called the proportionality limit. So this point A is a proportionality limit. Point A is called the proportionality limit. Okay, chalo. So now after point A to point B, so here, so the body will again, this B point, so let me write it here. So the B point is called the yield point or elastic limit, That means, so after B, like beyond point B, so the body loses the elastic property. Okay, so till point B, so the body retains or regains its original configuration, if we remove stress. So this point B is called the yield point or the elastic limit. So up to point B, whatever the stress or the load that you apply on the object, so if you remove that load, so the body again will come back to its original shape, original configuration. So beyond B, so the elastic property reduces. Okay, so this is all the theory concept. Okay, so beyond B, so the elasticity reduces. The elasticity reduces. Clear? So from here to here, so from point B till point B, the elastic limit, this is the elastic limit, the body will retain its original position. Okay, fine. So now after point B, so if you apply any stress, so the permanent change occurs. So here after beyond B, the permanent change occurs. Permanent change occurs in the body. Clear, guys? Understanding this part? Chalo. So now see from B to C point. So from B to C point, so where if you apply the load or the stress on the body, so then the body will regain its original, the body will not regain its original shape. There will be some permanent set. This is its original point. And finally beyond B, beyond C, if you apply the force, so the body will not, like you applied the force and you remove the force till point C. If you remove the force, so there is some permanent change occurs on the body. There is some permanent change. So here B to C region, so there will be some permanent change occurs in the body. So there is some permanent change occurs in the body. Clear? From here to here. So that means if you remove the load here, so the body will not regain its original shape. So no. So there will be some permanent change. So there will be some permanent set. This range is called the permanent set. Okay. So now you applied the load beyond C as well on the body. If you applied the load beyond C as well, so this D point is a maximum tensile stress, that is also called the that point D is the ultimate stress, we call the ultimate stress, or which we also call it as the breaking stress. The ultimate stress or the breaking stress. Okay. So here in this this is the maximum load a body can, this is a maximum load an object can withstand. An object can withstand. So after beyond this, if you apply any stress or load on the object, so what happens is, so the body starts to break. So the body starts to break. So this D point, see here, A point is a proportionality limit, B point is a yield point, and this is a permanent, this is a plastic, we can say the plastic region. B to C is a plastic region. Okay. The plastic region where the body will not retain its original position. Right. So, and then so D is the maximum stress or the ultimate stress or the breaking stress, where the maximum stress the body can withstand. And after that the body starts to crack, and then at some point it will reach the complete fracture. Okay, the fracture point E is called the fracture point. Clear? Understood this point? And so one more thing here you should understand, that is, so if these 2 points, see here, so if these 2 points are far, D and E, if they are far, so then the body will have the more what we can say, more ductile. The body is said to be more ductile. If D and E points are far, so then the body is said to be ductile in nature. So if they are very close, so then the body is said to be brittle in nature. Okay, so in the ductile materials, if you apply the stress, so it will not break after the maximum stress or the ultimate stress. Still it elongates. If you apply the force, still it elongates, and after some point it breaks. But the brittle materials, whenever they reach the breaking stress or the ultimate stress, so they break, they fracture immediately after this point, after D point. But the ductile materials will not break after the ultimate stress or the breaking stress. Clear? Understood this point? Chalo. So this is all about the stress strain curve. So let's understand again. Just let me brief this point. So see here, O2A region is a elastic region. So where the stress is directly proportional to strain. If you remove the load, the body will retain its original configuration. And A to B is also the elastic region. So up to the point B, which is the yield point or the elastic limit, so the body will retain its original configuration if you remove the force or the stress. And then C point, so beyond C if you apply the force, so the beyond B if you apply the force, the body will not retain its original position, so there will be some permanent set. And then D is the maximum stress the body can withstand, or the maximum load the body can withstand. So which is also called which we also call it as the breaking stress or the ultimate stress. And E is the fracture point. Clear? So this is all about the stress strain curve. So now let's go for the so the different nature of stress strain curve. See, so for the ductile material, as we discussed earlier, so the ductile materials are the one which can be drawn into thin wires, right? So the ductile materials are the ones which can be drawn into thin wires. Yes? Yes or no? Sorry. So thin, sorry, sheets, my bad, into sheets, my bad. So which can be drawn into sheets. Yes. So now see here, so this B to C is a elastic limit. Okay, we all sorry, B point is a elastic limit, A point is a proportionality limit, D is a breaking point. So this D, and there will be some point E, the fracture point, so they both will be bit far. D and E, the points D and E are far apart for ductile material. So D and E are far apart for the ductile material. Okay, chalo. So for brittle material, so this breaking point and the ultimate stress, so they both will be very near. D and E are very close. Those 2 points are very close. Okay, clear this point as well? Chal. So next, so the elastomers where the stress is directly proportional to the strain square, or the strain, we can write like this way. So the stress is directly proportional to the strain square. So which is nothing but, so it will be in the form of y is directly proportional to x square. So y versus x square graph if you draw, so it will be somewhat the parabolic shape, right? So like this. So the same stress strain curve you can obtain it for the elastomers. Okay, and for natural rubber, see, the beauty of natural rubber is, so the force, how much force you apply it on it, so it will again regain its original configuration. So this is the original configuration. After the removal of the load, so it again regains its original configuration. But the thing is, so it will not follow the same path. It do not retraces its path. Okay, it do not retraces its path. It do not retraces its path. Done. So the stress versus strain curve, if you observe, so this is the initial one. If you apply the load, this is a graph. So now after the removal of the load, so the body is following the different one. So this area under this one will give the energy wasted. So this is the energy wasted in cyclic. Okay, so this is the area under this one will give the what is the energy wastage in this process. Then clear guys? So there are four different nature of stress strain curve for the ductile materials. So the graph will be like this, where D and E points are far apart, and for the brittle materials, so they are close. D and E points are very close, and for the elastomers it looks like a parabolic graph. Y is directly proportional to x square. And then so for the natural rubber, so it regains its original position, but it do not retraces the original path. Okay, so it comes in different path. So the energy wasted in this cycle is nothing but the area under this loop. Clear? Done this part? Chalo. So let's move further guys. So we have got one question. See here. So these are not the options, these are the four questions. So which material has a greater Young's modulus? So which material has a greater Young's modulus? See, so if the slope is more, the Young's modulus will be more. Okay, so if the slope is more, then the Young's modulus will be more, right? So in this one, let's say this is a this is B curve. So here theta A and here theta B. So I could see that the theta A, this is closer to the y-axis and this is somewhat far. So compared to this one, yes or no? So then theta A will be greater than theta B. So here theta A is greater than the theta B, so that the Young's modulus of A is greater than the Young's modulus of B. So which material has a greater Young's modulus in this? So the A1. Clear? Chal. So which material is more ductile? So ductility property, how do you tell the ductility property? So if the breaking stress and the fracture point, so this is a breaking stress point and this is a fracture point. So D and E, so these two are far apart. D and E are somewhat far apart. So here this point is the D, right? And this point is the E, the last point is the E. So D and E, they are close. So the ductile one, so where D and E points are apart. So this is also the curve A, right? And then which material is more brittle? So I can say the second one, D and E are close. So the B one. And which of the two is the stronger material? So the ductile material will be the stronger material. So the A1. Clear guys? Understood this part? Any doubts here? So just have the look at the questions once. Done? So just let me have some water. Yeah, sorry. Chalo. So let's go further. So done this part? All the questions understood, right? See, stronger material A, how we are saying? So for whichever the one, the breaking stress is more, so that is said to be the stronger material. So for this one, the breaking stress is more. See here. So compared to this, this one has a more breaking stress. So because more breaking stress. Done? Chalo. So we have one more question here. So the stress strain curves are drawn for two different materials X and Y. So it is observed that the ultimate strength point and the fracture point are close to each other for material X. For material X, so the ultimate stress, so the D and the fracture point E are close. Okay, right. So and for the material Y, so they are far apart. So D and E, they are far apart. they are far apart. Okay, so then we can say that the materials X and Y are, so the first one is they are very close, brittle, they are very far, so ductile. So brittle and ductile. So the first one, X is a brittle and Y is a ductile. Option 3 is the correct one, brittle and ductile. Clear guys? Chal. So now let's come to the Poisson's ratio concept. So the Poisson's ratio is denoted by sigma. So okay, so it is denoted by sigma. So what is Poisson's ratio actually? When a material is stretched, when a material is stretched, its length increases, and so the diameter decreases. Yes or no? Its diameter decreases. Chalo. So let me show you here. So for example, this is a rigid support. So this is a rigid support from here. So we are attaching a material like this. Okay. So then we applied the load. We applied some force load so that the body has elongated like this. So this is a change in length. So this is a change in length. The delta L, we already know this one. This is a delta L, change in length. Fine. So the original one from here to here. So we can say that. So there is some diameter decreasing is there. So there is some change in the diameter. Yes or no? So we can write this is delta D, this is delta D, or we can say this is the whole thing. So D minus delta D. This whole thing is a D minus delta D. So let the original diameter be D minus delta D, which is the change in diameter, so that we get the final diameter. Yes or no? So there is change in length and there is change in diameter. So now the Poisson's ratio sigma, which can be written as, so the lateral strain, it's a lateral strain by the longitudinal strain. It's a lateral strain by the longitudinal strain. Yes. So we already know the formula for the lateral strain. So what is the formula for the lateral strain? So simply I can write, so here the diameter is getting decreases. So the delta D by D, the longitudinal strain means, so the change in the length. So the change in the length by the original length. So this is a formula for the Poisson's ratio. So minus delta D by D by delta L by L. Why minus? Because the final one will be less. So this will be less, minus delta D by D. It decreases, right? So that's why I'm keeping minus there. Done? Clear? So chal. So you have to remember this formula guys, or else you can also write this as, so delta R by R by the delta L by L also. The delta R by R by delta L by L. Clear? Done? Chal. So let's see the questions based on this. So the third question, try to do this question on your own. The increase in the length of stretching a wire is 0.05%. If its Poisson's ratio is 0.4, so then its diameter, what happens to its diameter? So first, what's the given information in the question? What is the given information? So the increase in the length of the wire is 0.05%. So that is the delta L by L is given 0.05%, and the Poisson's ratio sigma is given, so which is 0.4. Then so what happens to its diameter? So the diameter, so the sigma is equals to minus delta D by D by, so the delta L by L. Yes, so let me write here, so the delta L by L, right? Chal. So next, so here delta L by L is given, and then sigma is given. So I can write minus delta d by d is equals to delta L by L into sigma. So what is this one we got? So the delta d by d. So let me take the magnitude. So however it decreases because it is stretched, not compressed. It is stretched. If it is compressed, so its diameter will increase. So but it is stretched. Obviously the length increases, the diameter decreases. The diameter decreases. So how much it decreases? The delta L by L 0.05% into, so the Poisson's ratio which is 0.4. So which we can write it as 0.02%. So increase or decrease, so the diameter decreases. It's a reduce, increase you can cancel off. So it's reduces by 0.02%. Option 1 is the correct one. Clear guys? Done? Sure. So let's try this question on your own. So the next question, try this question on your own guys. First, so if the Poisson's ratio for a wire is 0.5 and the longitudinal strain in the wire is given 2 into 10 to the power minus 3, so then the percentage change in the volume of the wire is, so what is the percentage change in the volume of the wire? So that means the delta V by V we need. What is the delta V by V? Okay, so how do you solve this one? Can you guys try it on your own? First, write the given information. Sigma is 0.5 and then the strain, the delta L by L, the longitudinal strain they clearly mentioned. So 2 into 10 to the power minus 3. So chalo, so first can we write the sigma is equals to, so minus delta d by d by the delta L by L, right? So from here the magnitude of delta d by d is equals to sigma into delta L by L. So sigma is, so 0.5 into, so 2 into 10 to the power minus 3, right? So this one is longitudinal strain. So we have got it as 1 into 10 to the power minus 3 or simply 10 to the power minus 3. So now what they are asking, the percentage change in the volume of the wire. So how do you calculate the volume of the wire? So wire is of the cylinder. Wire is of cylindrical shape, right? So the volume will be equals to, so let's write in terms of length. So pi r square into the length L. Pi r square into the length L. Yes or no? So shall I see here? So the delta V by V is equals to, shall I write? So 2 into delta R by R plus, so the delta L by L, error analysis concept, right? So 2 into, so what is delta R by R? So this delta R by R, see here, I am going to take, so this is not the magnitude. So let's take, so minus delta D by D. So which is nothing but minus 1 into 10 to the power minus 3. So the delta R by R also the same thing. Okay. So 2 into, so minus 1 into 10 to the power minus 3. So what is delta L by L? 2 into 10 to the power minus 3. So which is, so 0. Yes or no? So 2 minus 2 into 10 to the power minus 3 plus 2 into 10 to the power minus 3, both gets cancelled. So this is going to be the 0%. So the option 4 is the correct one. Clear guys? Understood? Sure. So let's see the next question. So what's the question says here? There is no change in the volume of a wire due to change in its length on stretching. So that means the delta V by V is 0, they are saying. So the Poisson's ratio of the material of the wire is. So what is the Poisson's ratio of the material of the wire? So there is no change in the volume of the wire. Delta V by V is 0. So they are asking what is the Poisson's ratio. So same concept can you guys apply? So same previous question concept. Same previous question concept. First, same previous question. See, the wire is of cylindrical shape. right? So what's the volume of the cylinder? So the volume is equals to pi r square into the length L. So in place of r, if you can write this way also, d by 2 whole square L. So I can write pi d square, so pi d square by 4, 1 by 4 into L, right? So chalo. So shall I write the delta V by V? The delta V by V is equals to, so here if I apply the error analysis, 2 into delta D by D plus delta L by L, right? So here the delta V by V is given in the question 0. So I can write 2 into delta D by D. So plus delta L by L. So here I can write the delta L by L is equals to minus 2 into delta D by D. Delta L by L is equals to 2 into minus 2 into delta D by D. So now what is a question? Poisson's ratio we required. So Poisson's ratio is equals to minus delta D by D by delta L by L. Yes. So what is minus delta D by D? So let it be, in place of this delta L by L, I am writing minus 2 into delta D by D. So this one cancel, which is 1 by 2. So which is nothing but 0.5. So which is plus 0.5. So the option 1 is the correct one, guys. Done? Clear? Chalo, so that's it for today's lecture. It's a very short lecture. So we have covered so the stress strain curve and the Poisson's ratio. So we'll meet in the next lecture with a new chapter, that is mechanical properties of fluids, guys. So till then, keep studying. All the very best. Bye.